Okay. Hello, everybody. This lecture is devoted to Rosenbrock function and its minimization. Rosenbrock function is a two-variable function which is unimodal and is used generally to test gradient-based optimization problems. The general form of this function as a function of x and y, and it's equal to a, which is a constant, minus x all squared, plus b, this is another constant, multiplied by y minus x squared, and all the bracket is squared. The characteristic shape of this function is a like narrow parabolic valley, and really it is very interesting because it has only one global minimum and could be used with many other software, many different software like Python or like LabVIEW or others. Today we shall talk only about Rosenbrock. We shall plot this function on three-dimensional graph. We shall also optimize this function by using different optimizing functions and methods. And we shall also animate the behavior of this function when using the pyswarms in a two-dimensional plane and in a three-dimensional plane. So we begin. The first thing we begin with is to draw this function. We will initially draw it by using Python, by using matplotlib library. Because it is two-variable function, so we have to define the range of each of the variables, x and y. The range we suggest between -2 and 2, -3 and 3, which is within the bounds of the function. The function bound values is 5.12 minus to 5.12 plus. So within this range, we can select the values of x and y. In order to have an array, we used numpy a range function with the values -2, 2, and a step or interval between each two values is 0.15. We took this step the same for x and y. The range of both here is somehow different, no problem. In order to plot this function in a three-dimensional space, we need to create a mesh grid. So we use, as usual, numpy mesh grid function, where we pass X and Y coordinates, and we get as a result two new coordinates of X and Y. Each of them is two-dimensional. So now we have X capital and Y capital, as you see here, two-dimensional arrays. And as we know, the function of Rosenbrock is denoted by F. So the height Z, this is the third function, the third dimension, will be a function of X and Y, as you see here. So Z now represents the ordinate, the height, and it changes according to Rosenbrock function, and the plane is denoted or is defined by X and Y capital, which you see here. And now, in order to plot, we can use the plot surface function or plot wireframe function. It depends on desire. So at first, for coloring, we have got the hot color map and denoted it as CM. This will be passed as an argument to the plot surface. And we pass to the plot surface the three values, the three variables, X, Y, and Z, so that we shall have the plot complete. So from AX object, we call the plot surface function and pass to this function X, Y, and Z, and the color map equal to CM. We assign a limit to the third coordinate Z by using set Z limit function between 0 and 200. It depends. This is upon desire, as you want. Also, it is a common practice to assign a color bar aside the three-dimensional figure. So we used, or we called the color bar from the figure object. Here the figure, it is called figure from Rosenbrock, just to denote or to show that this figure is related to Rosenbrock. We call from it the color bar, and this bar here for the surface, it will explain the coloring from bottom to the upper point of the surface, and you can shrink it, or you can change also the number or the width of the color bar. I have given it number 5, and I have shrinked it to 0.5. So when we run this program now, we shall get a three-dimensional space, as you see here. This is the color bar. This is the maximum value 200. This is the range of X from -2 to 2. This is the range of Y from -1 to 3. And this is the height. Now, if I run it, I will get the same figure if there is no problem. Here is a comment. I didn't put here the hash, so the program cannot be run. I now will exclude it from the program. And now if I run it, I think we shall get the same figure. Here is the figure which I have got for the Rosenbrock. As you see, it is somehow similar to a value. The figure itself depends also on the values of the constants A and B. Here I have taken B equal to 10, as you see. B in the function here is equal to 10, B, and A is equal to 1. I didn't multiply it by any other figure. So this is the figure which I have got with two constants. Now I wanted to show you also the same figure by changing the value of B. B now is 100. This is really a common, very common number used with Rosenbrock. So B here is 100, but A is still 1. Other values are kept the same. So when I run the program now, I have got this figure here, as you see. It is really like a U shape, U shape of Rosenbrock. Also, if I try to rotate it within the three-dimensional space, it doesn't rotate. I added the wild letter with matplotlib notebook at the beginning of the cell here, and I think kept the same value for B equal to 100, and I displayed the figure and rotated it by the mouse. Now this is, you have to run it and then you can rotate it. If I run it now this is the figure which I take with the initial position. Now I can rotate it the way I like. Well, for example, now it is here, or like this. Here it is again, and so on. So, shortly speaking now, we have generated, or we have plotted the figure of this Rosenbrock differently. You can change the coloring, of course. Instead of having hot, you can write color map cool or varieties or what you want. It depends. The coloring is your choice. And we have rotated it with the required angle. And I think this is the most important to know about plotting. We shall see at the end of the lecture also how we can plot it, the same function, by using LabVIEW. Now also, for your knowledge, we want to show you 3 different methods and functions which are used by Python or SciPy Python to find the optimal minimum value. But before doing that, I tried also to show you how we can draw a contour in a 2-dimensional space for this function. So if you follow up here, we import NumPy as NP. We import matplotlib as usual, as PLT. We define X and Y or N and M arrays of values which represent the coordinates. And of course, we have to use the NumPy mesh grid function. So we call NumPy mesh grid function and we pass there the coordinates N and M as shown here. And now we express or we show our function Rosenbrock here given a variable called C. And now we, from PLT, which is the shortened form of matplotlib, we call the contour function. This is of matplotlib contour, and pass with this within this function the m variable m and the C function here. If we run it, we shall get this figure as you see. And also, it represents many contours with many different values will be. I didn't manage the different values of the levels of the values of the levels here. Just I wanted to show how we can create it. Also, I have created the contour with other range of values, not more, to show you that this could be done and how it affects the lengths of the or the values of the x and y or n and m coordinates, of course, has an effect on the distribution of the contours. Okay, I think now we know a little bit about Rosenbrock, and we want now to know how we can minimize it. Really, the process of minimization of this function is very easy also by Python, not difficult job, and it takes no time. It is a matter of seconds, and you will get the solution ready. So suppose in this first example here, we want to call the function minimize from the optimize toolkit. It is really a library from optimize library. We call we import the minimize function, and from the minimize function, by using it directly, we can find the minimum value of Rosen. Really, this is because the default function for the minimize function, the default method is the let me say a specific function mean or Nilder mean function. So when you ask minimize, it directly works with Nilder mean function, and you do not have to select another method except if you want to use specifically another method. So here, what we have done, we have defined the Rosen function. As you see, the variable is a capital X, which represents as a list which has two values X and Y, and now the expression in normal form 1 minus X squared plus 100, which is this is a B constant here, a constant equal to 1, multiplied by 1 minus X squared all squared. This is the general expression of the Rosenbrock. As you have the name Rosen here, so from the minimize function, you pass the name of the function itself. Look, if it is here capital letter, it is here given capital letter, Rosen. And also, it is required to give the initial values of X and Y, because this function is a two variable, so it needs two inputs, one for X and one for Y. I have given, for example, 2 and 2. And this minimize function will give you a value of the output, a variable which is called result. So if I ask the program to print result, as I explained to you once, this result means that there is a set of informative data given to you about the whole minimization process. So it gives you initially a message called optimization terminated successfully or not successfully, and it gives you also a logic expression if there is a success or a failure to the process, and it gives you the value, the minimum value of the function at the coordinate where there is a minimum. It is given a name fun. Fun here is equal to 0, as you see. It is an multiplied by an exponent to the power of -11, which means 0 value. And the coordinates are 1 and 1, x equal to 1 and y equal to 1, and other information to you as the number of iterations or the Jacobian values or the number of events, anyhow, maybe of interest or not. It is given to you by the program. You do not ask about it yourself. For us, the most important here is to find the minimum value of the function and the coordinates where the minimum occurs. So, as you see, this is 100% as we expect. Now, we shall also try to find the same thing, yes, by using another method, not Nildermead, by using the conjugate gradient method, which is a method also within the minimize function. So we call from SciPy, we import the optimize, and from the optimize, we call the minimize function. For your knowledge, I expressed the Rosenbrock function in a parameterized form here. Instead of 1 minus x and instead of y minus x here, I use x of 0 and x of 1. Of course, here x of 0 squared. Instead of a equal to 1, I have given it value of 5. So 5 multiplied by 1 minus x indexed 0 squared plus x indexed 1 minus x indexed 0 squared. All of them are squared. This is the parameterized form of the Rosenbrock function. So at the end, from optimize, we call the minimize function, and we pass to this function the function which you are going to minimize here, which is f, which represents Rosenbrock, and I have given the initial values of x and y 0 and 0. When I run the program, now I will run it. Yes, so we will have the value of the minimum value of the function, a number multiplied by an exponent to the power of -12, which is the same practically as the previous answer, and the coordinates where minimum occurs 1 and 1, which is also the same. So we have got the same answer by using the conjugate gradient method. Yeah. If you want to be sure, you can change, instead of 0 and 0, the initial guess values. I suggested, for example, for you number 2 and -1. And if we run the program, we will get, I am sure, I tried it, we will get the same answer. Here, the function minimum value is equal to a number multiplied by exponent to the power of minus 16, which is nearer to the 0 value, and the coordinates are still the same, 1 and 1. Of course, you can put any two values. Let me try, for example, 12, and instead of minus 1, for example, minus 5. What is going to happen? Run the program. As you see, we have got the same answer. The function minimum value is a number multiplied by exponent to the power of minus 14 at this time, and the coordinates are still the same, 1 and 1. So there is no problem with it. Everything is normal. Here also, I am trying to show you how we can use the least squares function method instead of function method. Yes, instead of using the conjugate gradient method. So again, I have defined my function, the Rosenbrock function. I gave it a name fun underscore Rosenbrock, for example, of x. I have given it to you in parameterized form. Intentionally, I put, for example, this term after the first term. I have swapped the terms so that you know there is no difference. It makes no difference at all. The value of a, I gave it 1 instead of 5. Sorry, 1 instead of 100, and 5 is still the same one here. And now I have to call, of course, to import least squares. So from SciPy dot optimize, I import least squares. Here, I have managed to generate an array, NP array of 2 and 2, and give it a name input. So the output here will be only 2 and 2. Two values, two start up values for x and 0 equal to and 2. And this input will be passed to the function least squares with the name of the function, which is called here fun Rosenbrock. And now when I run the program, we shall see what will happen. Yes, so the input, yes, here will be 2 and 2, and the value of the function will be about 0. It is 2.54 multiplied by exponent to the order minus 6. It is approximated to 0, no problem. And the value of the coordinates is also 1 and 1. So now you have a good idea how to minimize or find the minimum optimal value of the Rosenbrock by using 3 different methods. I think we can do this with more than 3, but I think you can do this by yourself. I have shown you the most common ways and as an introduction for this subject. Okay, now let us do another interesting thing, which is how we can animate the behavior of this function through the optimization process. In order to do that, we shall work with pyswarm library. Pyswarm library optimizes the function and gives you the optimum minimum value and the coordinates also. But in addition, it has the facility to show you how the swarms change their positions on the surface, which has 2 dimensions, or in a 3-dimensional space. I want to tell you that finding the optimal minimum and the coordinates where the optimal value occurs happens very quickly, as we have seen with other methods. It doesn't take a time. It is a matter of seconds. But the animation process takes some time. Sometimes it takes 2 minutes, sometimes it's 5 minutes, 1 minute. It depends on the number of iterations you select, you decide to work with. And also it depends really on the number of the particles which are included in the program. Anyhow, the work begins as usual by importing the libraries and the functions of interest, which are going to be used with the pyswarms. So first of all, you need to import NumPy as NP, because you eventually has to generate some arrays and to work with arrays. And you need to import matplotlib library because you need to, of course, animate the motion of the particles through the animation function, which is within the matplotlib. You need also to import the pyswarms themselves. And as an alias for them, you call it PS, from pyswarms, PS, as a shortened name. Also, we import from IPython a module display. We call it from the IPython, and import from there. We shall need the HTML function really, so that we can see or notice or visualize the motion on the notebook, because I'm working with the notebook. Yes. Here, import matplotlib library. I have used it twice. This is not needed, so I can cancel it. Now, from pyswarms, there is a special library within the function called the functions, and this functions includes single objects functions. There is a set of standard functions within the pyswarms functions, so you can easily import from there the function you want, such as Rosenbrock. So I imported the Rosenbrock function directly from the pyswarms. Of course, you can use it directly by expressing its formula, but it is easier really to work with the Rosenbrock imported from the pyswarms if you are going to work with the pyswarms. Anyhow, if there is time, I shall show you how we can work with Rosenbrock without calling it from the functions library. So again, from pyswarms, we call the utilities. This is a module there. There is another submodule called functions. In that function, there is single object, the variables, where we want to work with single object optimization problem, and import Rosenbrock. Also, the pyswarms includes an object there or function called plotters. It could be called from the utilities, and from the plotters you call the formatters, and from there you can call the animator if you want to customize the work of the animator, which is included there. I have also introduced this wild letter with matplotlib notebook in order to be able to rotate the plot, especially when it is in a three-dimensional space, but maybe I don't need it, I have left it. Now, in order to write the program, I have found it necessary to show you quickly how we can do this, although I have explained this to you previously. So I have imported pyswarms as PS. I have done this before. From pyswarms utils functions import single object as fx. Also, I have done it before. I can work without these things. This is additional work, not necessary now. But here, the third line is necessary. From pyswarms, you call the utilities. From there, you call the plotters. And from the plotters, you call the following. You have to import plot cost history. This is a function which is used to plot the cost, the minimum value. And during the process of finding the minimum value, there is, as we did with the gradient descent, there will be a values, intermediate values of the positions and of the minimum values of the cost itself, of the function itself. So you need to see how the minimum changes from a given value up to the minimum possible value. So we need to see this by plot cost history. You also need to see the particles of the swarm on the two-dimensional space, so you call the plot contour. And if you want to work with the three-dimensional option, you have to call plot surface. Really, in this case, I am going to work with the first two. The third one here is just additional, but we shall work with it today also. Okay. As usual, this Rosenbrock function is bounded and has a bounds between -512 and +512. So it is expressed here as a variable bounds, which is, as you see here, a NumPy array of a list of -515 for X and Y, and NumPy array for 5.15 for the X and Y also. So you have the bounds shown to you as arrays. The coefficients which you are going to introduce, I explained to you, C1 and C2, and the weight W. I have selected them .5, .3, .9. Don't worry about it. It is not difficult to manage it or to variate these values. Normally, the C1 and C2 are between .1 to .5 to .6, not more. The weight could be sometimes about 1 or a little bit more. So, of course, you may need to read about it and their meanings. This is useful, and I have explained this previously for you. Now we want to optimize the process. So from the PS, which is the pyswarms, we want to optimize a single object function. We are going only to optimize one function, not 2 or 3 object functions. So it is a single object function. We call the single from the PS. And there we call from the single global best particle swarm optimization, because there is also possibility to call local best pyswarm optimization. We are going to work with the global best PSO, and here for this function we have to pass the number of particles in the swarm. I told you this could be between 20 and 30. Here I'm using 50. Maybe it is not a law, but it depends. If you have a higher number here, the time taken to converge will be more, and the space taken by the program in the memory will be more. The dimensions are 2 because we have 2-dimensional process or variable. The options are the same as those constants which we have already selected, and the bounds are equal to the bounds which are the same which we have defined in the previous line. So, of course, don't worry, you will, if you are going to work with this library as a rule and as a for practice, you will be dealing with it easier because you will remember many of these names repeated, and the sequence is repeated, and what is changes only sometimes the number of particles or sometimes the bounds, because it depends on the function bounds itself, not more. And of course, these coefficients, you can change them upon desire as requested by the program. So now this optimizer, this set gives you a variable or denoted by a variable called optimizer. Now from this optimizer, we call the optimize function. And this optimize function asks us, what is the name of your function? It is named Rosenbrock because I have imported it here as Rosenbrock. Here it is, imported as Rosenbrock. So this name will be used. And the number of iterations I have suggested 300 iterations will be sufficient. Now this optimizer will give you an output which represents the best position of the particles on the surface, the final best positions, the best positions where the optimum occurs. And this cost gives you the minimum value of the function which is required. The cost or the minimum value is the same. So if you ask to print the position or to print the cost or to print both together, it will give you the X and Y positions where the minimum value occurs. But I told you also previously that you do not need to print them. This depends on you because the program will give it to you directly. As when the program is run now, we shall have them or by the program given specifically in a special manner. For plotting the particles while they are moving, because the idea here, remember, I want to tell you one thing here. Remember when we worked with the gradient descent. With gradient descent, we only took one point and changed the position of this one point until we reached the optimal point on the line or on the surface. And we have done that with examples. With pyswarms, we do not start the optimization process with one point. You start the optimization process with a number of points equal the number of particles. So if there are 20, you have to begin with 20 initial values. But these initial values are given by the pyswarms themselves. They are given randomly by the program, randomly. So we initiate our work with a random values of the particles, which is about 20 to 30 to 40. It depends on what you want here. And these values, start values, are positions on the space. And during the optimization process, they will move gradually from one position to another position to another position at every iteration which takes place. So for iterations equal to 300, we will have 300 different positions for every particle. And it is supposed that all the particles will move in a given manner so that they will converge at the end to the best value which describes the minimum of the function or the best coordinates where the minimum value occurs. So when we plot the cost history, so we use the history of the positions and the history of the minimum values, and we will plot it as a function of the iterations. In order to do that, from the optimizer, we call the cost history. Optimizer dot cost history means we obtain the cost history from the optimizer and we assign it to a variable called cost history. And now this cost history will be passed, as you see, within the function plot cost history. So plot cost history now will give you a drawing which shows how the particles are, which shows the value of the minimum or the intermediate minimum values from the initial value through the 300 values until it comes to the 0 or about 0 value. Now, to make it easier for you, here what we shall get. We shall get this figure here, as you see, which here the beginning from 0 of iterations up to the given number, which is 300 iterations. You can see how quickly and abruptly the cost function, which means the error, drops down through these values. This is the cost, through these values, and it reaches the 0 level. The error value is equal to 0 practically at iteration, maybe number here 50, here 0. So here maybe the first 2 or 3 or 5 iterations, you get the minimum value. As I told you, this is very quick work, quickly convergence, and this is the same result which we get when we found the minimum value by using other similar functions which we have done before, half an hour ago maybe. So when we plot the cost history, we plot the minimum value of the function and how it changes. And we found that this function, as you remember, has a minimum value equal to about 0. And here is the 0. And you see really it is indeed a 0 value, and it takes a limited number of iterations to converge to this value. But what is also interesting here is we want to see the 30 or 40 or 50, I think I have put there the number of 50 particles. So we want to see the 50 particles, how they change their positions from the initial value until they reach the final X and Y values exactly where the minimum occurs. So in order to see that, we need a plotter which plots this motion. So from pyswarms, we call the utils, and from the utils we call the plotters and the formatters, and from there we call a function really called the measure, and another function called the designer. The measure and the designer are functions used very often to customize the mesh and to customize the sizes of the coordinates of the plane surface. Initially, or let me say, the default values of the measure and the designer, I think in most cases, you may need to change them and to customize them depending on the function itself and the expression of the function itself and the limits of the function itself. So suppose I have the designer. The designer in the pyswarms limits the x and y coordinates by 1 and minus 1, 1, minus 1, 1. This is for the x coordinates, this is for the y coordinates. And if you want to also know about the z coordinates, it was also given minus 1 and 1. So the initial values, the default values of x and y and z are minus 1, 1, minus 1, 1, minus 1, 1. If you want to change them, you can change like this. You go to the designer, you call the designer. Within the designer, there is limits. Here you can put the limits you want. As you see, they are expressed as a list of tuples. The first tuple minus 1, I put 2. Minus 1, I put 2. So x between minus 1 and 2, and y between minus 1 and 2. And the label of these axes, x-axis and y-axis, they are given these names. So I have decided the x value and the y value here of the x value minus 1 to 2, and the y value also from minus 1 to 2. And this really is done intentionally because I know now in advance that this function converges to the minimum for x equal to 1 and y equal to 1. So 1 and 1, x equal to 1 here, y equal to 1 here. This is the level of y equal to 1. And this is the level of x equal to 1, where they converge. So I need to define the limits of the coordinates so that this point is given in an appropriate position on the surface. So as you see here, I have suggested the limits to be minus 1 to 2, minus 1 to 2 for x and y. And now the designer is given a name or a variable, new variable called my designer. And this my designer, the new value here, must be passed to the plot contour, which is going to plot. So when you go to the plot contour function, you will find there the designer is given or assigned a new value called my designer. The same thing applied for the mesh or the measure, because also you can customize the levels of the measures and the steps between these values or these levels. In this case, especially, I didn't customize the measure and I didn't use the measure to show you that we can do without it, but we shall do with it a few minutes later or 10 minutes later. So now I call or I use the plot contour function, and in order to plot, I have to call the position history which is taken from the optimizer. So from the optimizer, I call position history and assign it to a variable called position history, which will be now within the plot contour. So the plot, of course, you can do it alone. I can write here before, here, optimizer dot plot history. I assign it to a variable called position history, and this position history will be written here alone. Okay, the designer also now is assigned a new value called my designer. The animator is assigned a new value called my animator. So this means that I have changed something with the animator. What I have done here, I have called the animator, repeat equal to true. I mean that when the iteration beginning from 0 to 300 finishes, this whole process could be repeated again and again. So repeat, I have given it a true value, and the time delay between repeats, I given it 200 milliseconds. You can give it any other value, you higher or slow as you want. You can watch, if you want to watch it slower, you can give it 400, 500 milliseconds. It depends on you. So these changes means that I am going to use new values for the animators. This is a customized values. So the animator now is given another name, my animator, and this my animator now is assigned to the value of animator. What more also? Mark equal to 1, 1. Mark is the point which I suppose I expect that there will be the convergence. Here it is 1 and 1. Because I expect that and I know that before and I want to see if it happens truly, I can also in advance ask the contour or plot contour to show me this point, and it will be shown to you as an X multiplying sign as an X with a red color. But it will be shown at these coordinates 1 and 1, which I suppose that this is the final point, so that to be sure that the program is working well or not. Is there a deviation or a big deviation from the expected value? Now we know what is the mark also. So we have managed to customize the designer to a my designer value and the animator, and the mark is equal to 1, 1. And now we want to show the whole process, PLT plot. After that, I want to save the whole process of animation. This process is called in a variable called animation or anim, as to shorten it. Anim dot save, I call a function save. I gave it a name, plot Rosen GIF. This is the type of the function. And the writer, which will write the plot, is image magic, which is already installed in my computer. I have installed it. And also I have imported the HTML. You remember I told you that I needed HTML. I have imported it, and I passed through this function, this animation, anim, to JavaScript HTML function, so that I can see the animation on the notebook directly without saving it. This is interesting here, because if you want to run this program and the number of iterations is long enough and the number of particles is big enough, it may take 5 minutes or 2 minutes or more to finish the process. So you can run it and go do your work, and when you come after 10 minutes or like as you want, you can go here to the program and see here this function, this setup here, and this function shown. Here is the point or the x, which is in red, which is 1, the height, and 1 x and 1 y. This is the expected value. If I run the program now from here and look at it, all the particles now are moving and moving and coming closer and closer until all of them converge to this point. This means that the work is perfectly done. And I have shown it to you quickly. It doesn't take any time because I used the HTML function. Moreover, if I go to the plot Rosenbrock, which is a function already now, which is the name of the plot, which I have saved here. If I go to the, let me here write it again, for example, what it is name I have forgotten, plot Rosenbrock. Here, I want to see it, plot Rosen dot Jeff plot Rosenbrock. Yes, it is. And I will find it in a file already saved there. Here, plot Rosenbrock. I am not sure it is or not. No, it is a name given to yes, it is, but I don't want to show you this one. I want to show you another one. This is already saved before. Now, if I run the program newly and go there, I will see the same picture as I've seen here. Let us do it together. So I cancel this. Now I will run the program. As you see now, this asterisk means that the program is running. Now I have got quickly the minimum of the function, which is 0. If you go up a little, and you will see that the cost value at minimum is equal 1.65 to the order of -5, which means 0. This is the minimum value, 0. The best position is 0.99, which means 1 and 1. So practically, I have got what I want very quickly. But this is the situation which I have. Here is minus, here is 1, and here is 1. I didn't change it. It is not changed with me. If I go here, I have run the other program. I am sorry. So I want really to show you the program which I have illustrated to you. Let us go back and see it to be sure. This is the iterations 100, yes. These are the yes, yes. Now let us run this program and see. No, no, it is not my program. This is this is still running. My program is still running here, as you see. It is still running. Look, I told you it will take some time. I am sorry that for this reason I wanted to skip this, but we have to wait about 2 to 3 minutes or more. Be patient, please, to be sure that it is working. It is still there. Yeah. Anyhow, the process, let me talk with you while it is working. The process of animation really is very often used by data scientists or engineers uh, because really it gives you the real picture during a dynamic process and shows you how everything is going step by step. You feel confident and feel happy with this. If you do not see this and you get the final result, it is okay, but it doesn't give you that pleasure as you get it with animation. So the process of animation really is an important step, but it is usually given as a final step of work because sometimes you do not have time for it. Sometimes you feel that it is not necessary to do that. But as a practitioner in this area, I think you must know the technology and you must know the basics of how you do it. Anyhow, until it gives the result, I want to tell you, doing animations with pyswarms is something built on the matplot library itself. It is not the animation which is you do with working alone or directly without pyswarms. If you want to carry out animations without pyswarms, so you need to work with a special function, a special class in matplot library called func animation. And this func animation to work requires from you to create an object to make an initial function, to create and design an update function, to decide many things and pass these variables to the uh, to the func animation function, and then you will, it is still working. It doesn't, it only has given me the result here that the minimum value is 5.6 with an exponent to the order minus 11, and give me truly that the coordinates of x and y are equal to 1 and 1. Here, if you see in the program here, I have forgotten to ask the program to plot the cost and to show me how the cost changes by time. I have asked directly to plot the contour. If I go to the program, it is still going on. It doesn't yet finish with the plotting the contour, as I told you. So let us wait a little bit to be patient for that. But going back to my talk, so you need to work with the func animation func class, and you have to know what it requires in order to animate without using the pyswarms. Specifically for this case, I am going to show you how we can do that when we carry out animation for three-dimensional space. For two-dimensional space, I found it is acceptable to show you directly by using pyswarms, so that to acknowledge you with the pyswarms here. And I hope in the next lecture, because I think this lecture becomes long if I work with this today. So in the next lecture, I shall begin my talk with you with some summary about today's lecture, and then I shall work with you on optimizing and plotting the pyswarms motion in a three-dimensional space in order to see how all the particles really converge to the value of 1, x equal to 1, and to the value of y equal to 1, as we shall see now with the pyswarms plot contour function. Anyhow, also in pyswarms, they call it plot contour function, but in matplotlib library, it is not really plot contour. You can use there a function called AX contour or PLT contour. So they are different also by name, and they are different by their structure inside, and the arguments which you pass, to the PLT or AX contour of matplotlib library are not the same arguments which you can pass to the plot contour as we have done here, to the plot contour here as we have done here. Yes, it takes a lot of time, but we have to wait. I think it is not that much to wait, another 2 minutes maybe, or half a minute, because the program is responding. It gave us the values, but the drawings, not yet. We shall have here 2 drawings, 2 plots. One of them, the plot, which we will have instantaneously, and the other one which will be saved by using HTML. So be patient, please, and you will see it now. Okay, it is finished. So now, here is the case. Now, if I run the HTML from here, you shall see how the particles move, and they collide at the level 1 and 1, which means that this is very excellent work and everything is okay. You see, convergence is 100%. The red crest here, the red X here, you see, and it is covered by all the particles, which means all the particles found the best convergent value. This also figure, which is up, works well, but it works when I run the program. If you want to see it, you can go to the plot Rosen GIF. Now, if we go to the plot Rosen GIF, let me go to the another way, maybe to the PC. Where is my PC? If I can. Yes. If I go to the PC and we go to the C, and from there to the users, to the del. In the del here, we can see this function. Plot Rosen GF here. Now, if I run it from here, you shall see the same picture. So you have 2 ways. If you haven't the chance to watch it directly when it is just finished, you can go to the file where the result is saved as GIF file, or you can see it directly on the notebook with the HTML function. Okay, I hope that you did not lose your time. I hope that this was very useful to you. We have, in summary, acknowledged you with the Rosenbrock function, with the expression in a parameterized form or in a normal form. We have plotted this function and shown you how we can rotate it, how we can see it differently depending on the parameters. And at last, we have also shown you how we can animate this function on the plot on the surface by using pyswarms. I think the lecture has become too long. I have to stop today. In the next lecture, I shall try to show you also with more detail about this function and how we can animate the process in three-dimensional space, and how can we do analog works by using LabVIEW. Until then, I hope to see you again, and that you will be safe and happy. Wishing you the best, and goodbye.